Swayam Prabha. Digital India. Educated India.
Okay, so we will continue with the approximation algorithm. So, what we saw in the previous session was for vertex cover, the simple greedy algorithm of finding the highest degree and deleting it continuing does not give you constant ratio approximation algorithm. I did not prove it, that is, think about it. Maybe we will get to it tomorrow, but I said that it actually gives you a log n ratio approximation algorithm. What that means is the solution produced is at most order log n times the optimum, but I gave you another algorithm which is simply find the maximal matching in a graph, pick both endpoints of the matching edges, that will cover all the edges and its ratio is at most twice the optimum. Is it obvious that why I should pick both endpoints? Because I know to cover the matching edges, one endpoint is enough. There are other edges, right. So, your graph, I find the maximal matching. How is the rest of the graph? Well, the rest of the graph, there may be a lot of vertices here. There cannot be any edge here because it is a maximal matching, but the edges will be like this. Also, there are edges like this, right. You need to cover all of these edges. So, that is why just picking one endpoint is not enough, because the graph is not just the matching, the graph is a lot more things. So, but picking both endpoints is enough because that covers all the edges, and we argued that you need at least one from each of the matching edges and you are picking two. So, it is at most twice the optimum. Okay. So, first I will give you another ratio 2 approximation algorithm through linear programming, and then I plan is to move on to the travelling salesman problem, and we will look at approximation algorithms for that. Okay. So, recall how we formulated vertex cover as a linear program, right, minimum vertex cover. As integer linear program. How did we formulate this, right? So, I am trying to find a subset of vertices. So, what should be the variables for the linear program? Exactly. So, I have a variable for each vertex. 1 means I am picking it into the solution, 0 means I am not picking it into the solution. Okay. So, that is the starting point. What is the objective function? What is it I am trying to minimize? Sum of xi's, right. So, minimize summation xi. So, my graph, and let us say v is 1 to n. Then I want to minimize summation xi. I want to minimize the number of vertices I pick into the solution. What is the constraint? Xi plus xj. What are I and j? For all I, j in A, E, what do I want? Xi plus xj is greater than or equal to 1, right. For any edge I j, at least xi must be 1 or at least xj equal to at least 1, right. And then I had more constraint. What are the constraints on the xi's? They are either 0 or 1, right. This is exact formulation of minimum vertex cover, okay. Because if you pick any solution to this, wherever I have put 1, take it into my set, and that would be a vertex cover, and you pick any vertex cover, you can model it as you could set the variables to 1 and it will satisfy all these constraints. Okay. So, I said in the previous session that linear programming can be solved in polynomial time, okay. But this is not linear programming, this is an integer linear programming, because I have this constraint in that variable should take integers, what do I know about integer linear programming? Are they solvable? Is it solvable in polynomial time or is it NP hard? Just stare at it. We actually proved that integer linear programming is NP hard. What did we do? We reduced from vertex cover, right? We have actually given a reduction from vertex cover to integer linear program, right? Given a graph, I created an integer linear program such that G has a vertex cover of size at most k, if and only if this ILP has value at most k. Right, the decision version of the integer linear program would be, given the integer linear program is the optimum value at most k, because it is a minimization problem. Well, we have actually reduced vertex cover to this. So, we have actually proved that integer linear program is NP complete. NP hard, NP is obvious because any solution would be a witness, you can verify. Okay. So, we have actually proved integer linear programming is NP hard. We have actually by reducing vertex cover to this. Now I want to use this somehow to get some approximation algorithm for vertex cover. Remember, that was our goal. Okay. So, let me just so you have one more problem for your NP complete kitty, that integer linear programming is NP hard because we reduced vertex cover to this problem, that is a known NP hard problem. Okay. So, now I am going to use, so I want to use this somehow, this formulation to give an approximation algorithm for vertex cover. Now, suppose I relax this constraint and say I want them to be integers, instead I just say xi greater than or equal to 0. Okay. So, instead of this constraint I put this constraint. Okay. And I also want xi's to be less than or equal to 1, but do I really want to put that constraint? Is that necessary? Xi less than or equal to 1? Just look at this LP, right? This is my LP. Do I need the extra constraint that xi's should be less than or equal to 1? Why not? You are trying to minimize the sum. So, if I solve this, would my optimum solution, will it necessary, is there a reason to make some xi greater than 1? No, because I have to just satisfy this constraint of xi plus xj is greater than or equal to 1. So, if some variable goes above 1, bring it to 1, it will satisfy this constraint and the objective value will go down. So, even without the additional less than or equal to 1 constraint, this is a linear programming relaxation of vertex cover. Now, this I told you that actually you can solve in polynomial time if you do not have this integrality constraint, right. So, let me solve that LP in polynomial time, right. So, I am going to say another approximation algorithm for vertex cover. Step 1, solve the LP relaxation. Right, solve the LP. What do I mean by this? That just formulate this LP and give it to some LP solver, which will solve in polynomial time and give the optimum solution for this, right. Now, I want to pull from this solution some vertex cover. So, what would be a problem in the solution? You may have some fractions for the variables, right, because I do not have integrality constraint. So, when I solve this, the LP's will solution will say, okay, take x1 equal to 1 by 3, x2 equal to 3 by 8, x3 equal to whatever, it will give you all that and say this is my optimum solution, okay, which meets these constraints, and I want to pull out some subset of vertices and argue that that is a vertex cover and it is at most twice the optimum, that is my goal. Okay. So, what is a natural thing to do? So, this LP gives you some fractional solutions. Now, I want to do some rounding to get a solution for vertex cover. So, what is the natural thing to do? If it is 0.2, what should I do? 0. Okay. So, let us try that. So, solve the LP relaxation and let us say I get some optimum solution which is x1, x2, xn, and this is what minimizes summation xi, right. That is what LP will give you. Now, so let x prime I equal to 1 if x I prime star is greater than or equal to half and 0 otherwise. Okay. Seems like a natural thing to do. So, I solve the, because LP is solvable in polynomial times, if you throw away the integrality constraint, I can solve in polynomial times, solve it. Only problem is it is going to give you some fractions, and whenever something is greater than or equal to half, I round it to 1, otherwise round it to 0, and I got some x I prime. So, whenever x I prime is 1, I put it in my vertex cover, and 0 I put it in my output. I have not proved it is a vertex cover. I will put it in my vertex cover, and whenever something is 0, I do not put it in my output. So, okay. So, now I am going to say output right S is equal to set of all I in the vertices such that x I prime equal to 1. It's very simple algorithm, solve the LP relaxation of a vertex cover. Whenever some variable gets greater than or equal to half in the optimum value of LP, take it in your solution, otherwise do not take it in solution. Now, I want to prove two things. What do I want to prove? What are the two things we need to prove? S is a vertex cover, actually S covers all the edges, and the value of S is not too far from the optimum. Okay, I will actually prove that it is at most 2 times the optimum. Let us see. So, claim 1 is S is a vertex cover, and claim 2 is size of S is at most 2 times minimum vertex cover. Okay, claim 1. Suppose not, what does that mean? There is some edge which is not covered, right. That means there exists some alpha beta in E such that x alpha prime is 0, x beta prime is 0, right, because I picked up all vertices whose primes are 1. What does x alpha prime is 0 means what? X alpha star is less than half, right. That is why I rounded it down. X beta star is less than half. What does that mean? It is not possible. Why not? Because x alpha star plus x beta star is less than 1. No, star was a feasible optimum solution. It satisfied this constraint. For whenever there was an edge, the sum must be greater than or equal to 1. So, at least one of them must be greater than or equal to half. They would have been rounded. So, S is a vertex cover. Now, I want to show that the number of vertices I picked is at most 2 times the optimum. Okay. Okay. So, claim proof of claim 2. Okay, let Z star is equal to summation x I star, right. This is the optimum solution of the LP relaxation. And what can you say about this and minimum vertex cover? What is minimum vertex cover? If I do not put this constraint and if I put this constraint, then that optimum solution is minimum vertex cover, right, because if I actually put the integrality constraint, then that is exactly the formulation of vertex cover. So, then summation x I would be minimum vertex cover. Now, I relaxed it. So, will it go down or go up? It is a minimization problem, right. So, in fact, if you see the integral solution is also a solution of this, right. The minimum vertex cover is also a solution, but now I have relaxed it. This is a minimization problem. So, it will actually go down. This is less than or equal to. Why? Because this is, I solve this with x I x j greater than or equal to 1 and x I greater than or equal to solve 0. This is a solution to that. optimum solution, whereas this is a solution to this, right. Any solution here is also a solution here, right, and now I have relaxed it. So, even I may get even fractional solutions and I will get this value could become smaller. Okay. So, minimum, so Z star is less than or equal to minimum vertex cover. So, one thing I forgot to highlight, see we are trying to compare the solution obtained by the approximation algorithm with the optimum, but I do not know the optimum, right, but I will compare it with some bound of the optimum. So, what we in the matching thing we said optimum must be at least the size of a matching, and we use that bound to do our comparison. Here I am saying optimum is at most this LP objective value, LP relaxations objective value. Okay. So, now I need to prove claim 2 after establishing this. So, what is cardinality of S? This is exactly summation x I prime I equal to 1 to n, right, because whenever it was 1 I picked it into my S, whenever 0 I did not pick it. And I claim that this is at most 2 times summation x I star, right, because what is the connection between x I star and x I prime? Whenever x I star was greater than or equal to half, I made it to 1, and whenever it was less than half, I made it to 0. So, in the worst case, if everything was half, I have just made them to 1. So, I would have at most doubled this summation x I prime. And what is summation x I prime star? I just proved this is at most 2 times, that is exactly what I wanted to show. So, here is another 2 approximation algorithm for minimum vertex cover. We saw one where find a maximal matching, pick both endpoints of every matching edge, and here it says solve the LP relaxation and just round it up. Okay. Now, the nice thing about the LP algorithm is the following. Think of the generalization, the weighted generalization. Suppose I have every vertex has some weight. Okay. Now, I want to find a minimum weight vertex cover. Okay. I want a subset of vertices that cover all edges. Among all subsets, one which has the total minimum weight. Now, the matching algorithm will not work, because I said out of these 2 endpoints, you do not know the weights of these vertices, there are some complications there, but the LP algorithm will work very naturally. So, how do I formulate the weighted vertex cover problem as a linear program? That is it, minimize summation Wi x I, everything, nothing else changes. Minimize Wi x I subject to this constraint with this integrality thing, and I relax it, same algorithm, do this rounding. Now, the argument would be S is a vertex cover will follow, and to show that not cardinality of S, but now I want to show that this weight of S is summation Wi into x I prime. X I prime is at most Wi star. So, that is this is everything remains the same. You can just go back and do the whole thing. So, also for weighted vertex cover. Okay, there are a number of ratio 2 approximation algorithms for weighted vertex cover, and improving the ratio beyond 2 is a long standing open problem. Okay, good. So, now I am going to move on to the traveling salesperson problem. So, the TSP problem, recall your input. we will assume the graph is complete, right. If it is not complete, then you just add missing edges with some infinity distance, and you had distance on the edges to natural numbers, and output Hamiltonian tour, a tour that visits every vertex exactly once with min cost, min distance, whatever. So, one thing to keep in mind, the NP hardness theory was all for decision problems, right. We said that. Approximation algorithms is for the optimization problem, because there is nothing to approximate a decision question. Decision question gives you a yes or no. What is that to approximate it? Whereas here, I mean, so the motivation is the decision versions are hard, so the optimization versions are even harder, and we are now going to look at, because that is what we are more interested in, the optimization versions. But we can, if we solve decision version, you can keep calling it and solve the optimization version. So, approximation algorithms for the optimization version. Okay. So, here is a striking first theorem. Unless P equal to NP, there is no polynomial ratio approximation algorithm possible. Okay. This problem is so hard. For vertex cover, we had ratio 2, ratio log n kind of approximation algorithms. Here I am going to say that you really cannot approximate it to any polynomial ratio. Of course, unless P is equal to NP, right, because P and NP are same, you can actually solve it in polynomial time. So, the way we will show is that it's actually, it looks big, right. How can you say that there is no polynomial approximation algorithm? We will show that if there is an alpha the Hamiltonian cycle problem can be solved in polynomial time. So, we already saw that if you have an algorithm for a TSP, you can solve Hamiltonian cycle problem. Remember, that is how we reduced, how did we show TSP is NP hard? We said, it is even more general than Hamiltonian cycle problem. So, if you have a polynomial time algorithm for a TSP, you can solve Hamiltonian cycle problem, right. That is what we did, the reduction. We added some weights and we proved it. This is saying something stronger. Even if you have an approximation algorithm for a TSP, I can solve the Hamiltonian cycle problem. Okay. So, if there is an alpha approximation algorithm for a TSP, Hamiltonian cycle problem, I can use that to solve it, and hence P will become equal to NP. Okay. So, this is what we are going to show. So, we will actually give a reduction from Hamiltonian cycle problem to this problem, but with a slight twist. Even if there is an approximation algorithm here, I can solve the Hamiltonian cycle problem. It is actually very simple. I mean, it looks surprising and hard, but it's so how. So, we are going to do. So, we start from a Hamiltonian cycle problem, and we will reduce to our TSP problem, but here the reduction is slightly not the usual kind of reduction we are used to, where this is yes if and only if this is yes. Now, here we are saying even I can use an alpha approximate algorithm to solve a Hamiltonian cycle problem. Okay. So, it is very simple actually. So, you are given a graph where I am trying to find Hamiltonian cycle problem, Hamiltonian, whether it exists, whether the Hamiltonian cycle exists or not. I will construct a TSP instance. What do I need for a TSP instance? I need distances on the edges. It is a complete graph and with distances on the edges, right. So, I will use G and my D will be defined as D of I j equal to 1 if I j is an edge. Otherwise, 2 is what we used in the earlier reduction and said that this has a Hamiltonian cycle if and only if there is a TSP tour of distance at most n, right. Now, I am not going to use 2 because now I want to use an approximation algorithm to get something, right. Suppose, so we assume an alpha approximate algorithm. Right, for TSP, not an exact algorithm, but some approximation algorithm I have, right. Okay. Let me put the weights and then you will see. For edge is not there, what I am going to put? I am going to put a cost of alpha into n plus 1. Okay. See, you told me there is an alpha approximation algorithm, right. So, now I will put a cost of alpha into n plus 1 whenever the edge is not there. So, now what is my claim? The claim is, well, one direction, if G has a Hamiltonian cycle, then the TSP problem has a cycle with of length total at most. No, if it has a Hamiltonian cycle, if G has a Hamiltonian cycle n, right, there is a cycle of length n, we know that. Let me write the claim and then I will come back to how we are going to use this. Else, any Hamiltonian cycle, so let us actually call this G prime, right. Of G prime has length strictly more than alpha n, right, because it must use one of these edges. Okay. So, this claim is clear. If G has a Hamiltonian cycle, then the same Hamiltonian cycle will exist in G prime with the total cost at most n, because any edges of the original graph have distance 1. If G does not have a Hamiltonian cycle, G prime has a Hamiltonian cycle, because G prime is a complete graph. It will have lots of Hamiltonian cycles, but all of them will use this edge, an edge of this type, a non edge of the graph, right, because G does not have a Hamiltonian cycle. So, its length would be strictly more than alpha n. So, we have made a separation. Okay. So, now you want to know whether G has a Hamiltonian cycle or not, that is our claim, right. So, now I translate this and give it to my approximation algorithm, right. I do not have an exact algorithm. Now, approximation algorithm, if G has a Hamiltonian cycle, will produce a cycle of length at most alpha times n, because it is an alpha approximation algorithm. And if G does not have an Hamiltonian cycle, it will produce a cycle of length greater than alpha n. So, I can get, so if G has a Hamiltonian cycle, the approximation algorithm will produce a cycle of length at most alpha times n, but there are no cycles of length at most alpha times n except the original Hamiltonian cycle. So, somehow I can, I have played around with my distance, so that I can even use an approximation algorithm to get a to use it to determine whether G has a Hamiltonian cycle or not. So, the if and only if claim is slightly different here, but I have room to play around here, where I have put a really large weight, so that even an approximation algorithm will actually produce a Hamiltonian cycle. If G has a Hamiltonian cycle, the approximation algorithm is forced to produce a Hamiltonian cycle, because G is Hamiltonian cycle, because its length has to be at most alpha n. There are no alpha n length cycles except the original Hamiltonian cycles. Okay. So, that shows the proof of this, that if you have an alpha approximation algorithm, I can use that alpha approximation algorithm for TSP can be used to solve the existence of R naught of the Hamiltonian cycle in a graph. So, what does that mean? That any approximation algorithm is ruled out for a TSP. Well, what do we do?